Hey Charles, welcome to the next lesson.
Hey, Michael. Thank you for welcoming to the next lesson. What is the next lesson?
So, I don't know, can you read it?
I can read some of it. I can't quite see all of it. Ha! I get it.
So, yeah, the topic is partially observable MDPs, but I made the MDPs partially observable.
Brilliant.
Kind of fell off the bottom of the screen. So, yeah, so this is the idea of talking about Markov decision processes like we've been talking about, but ones where the agent has to make decisions based on what it can see of the Markov decision process, not necessarily the true and current state.
Yeah, we talked a little bit about this in the old machine learning class, didn't we? But just a little.
Okay, all right. Well, so then we're going to get a little bit more into it, maybe. I don't know. What did we talk about last time?
I don't know. I don't remember. Just that I think we mentioned that they exist.
Okay, well, so we're going to talk about how they work. So here are the quantities that make up a POMDP. We have a set of quantities that are actually just an MDP. There's a set of actions and states and transitions and rewards. But the thing is that that MDP that is inside the POMDP isn't directly observable to the agent. And instead, the agent has to make its decisions based on the observations that it makes. So this Z stands for observations.
Or observables.
So it's a set like S and A. And then we need some kind of function that connects the states and the actions and the observables, or actually just the states and the observables. And we're going to write that as O, which is the observation function. What O consists of is a mapping from state and observation to the probability of actually seeing that observation, given that the agent is currently in that state S.
Okay, that makes sense. So there's a true MDP, and what makes the MDP really, I don't know, an MDP is really the state. The key thing has always been what state are we in right now? And what you're saying is that with a POMDP, you never actually know what state you're in. And so you get these observables or these observations, and that's what you see. And that gives you a hint about what state you're in, but it doesn't necessarily tell you everything. So it's a concrete example of that in the real world.
Well, in the real world, I mean, in the real world is like this, right? So when you're, I'm talking to you, and some aspects of the state of the world in Atlanta are actually relevant and important to me, like whether or not you have ice cream. But I can't directly observe that. I have to infer the presence of ice cream indirectly from whether or not you're taunting me.
But I'm always taunting you. But I think I get your point. Okay, that's fair. That makes sense.
Yeah, I mean, you could taunt me about ice cream, and that's not a perfect indicator that you actually have ice cream.
It's true. Sometimes I just taunt you for the fun of it.
Exactly. So what I need is some kind of observation function. I need to be able to predict, given whether or not you have ice cream. So let's say, given you have ice cream, what's the probability you taunt me? Which is very close to 1.
Mm-hmm.
And given that you don't have ice cream, what's the probability that you taunt me? And that's much lower, but not 0.
But still close to 1.
Well, you won't taunt me about ice cream when you don't have ice cream so much.
That's true. Also, when I have ice cream, you can hear me smacking.
Smacking? Oh, making mouth sounds. Well, again, that's a kind of observation. So smacking is a kind of observation that, again, is indicative of, but not a perfect indicator of, whether or not you've got ice cream in your mouth.
Okay, fair enough. All right, so I think I get that. Okay, so POMDP basically has an MDP inside of it, and you can't see all of it. And in particular, the part you can't see is S and maybe T.
The T relates S and A, right? The T says how, given that you're in a state and you take some action, what state do you go to next? But of course, you don't really know what state you were in, and you may not know what state you ended up in because, again, you as the agent have to make decisions based on what you can see.
Okay, fair enough.
Great. Now would be a good time for a transition to the next slide if we knew what it was.
Well, do we even know which slide we're in?
All right, Charles, let's do a little quiz just to solidify this idea of POMDPs in your mind and this notation that we're using.
Yay.
So what we're going to show is a useful fact, which is that POMDPs are a generalization of MDPs. And in particular, anything that you can represent as a MDP, you can also represent as a POMDP. You can build an equivalent POMDP out of the same pieces. So let's do that. So imagine that we've got an MDP consisting of state, action, transition, and reward. And we need to explain how we're going to create a POMDP out of it. And for a POMDP, you need to specify the state, action, observables, transition, reward, and observation function. And I'll give you a hint. The states of the POMDP are just going to be the same as the states of the MDP. The actions of the POMDP are just going to be the actions of the MDP. The transitions are going to be the same. and the rewards are going to be the same. And you now have to define what are the set of observables and what is the observation function that makes the POMDP act just like the corresponding MDP.
Okay, I think I can do that.
Cool. Just because you can observe things partially, that means in principle you might be able to observe things completely. And so that's what you need to show me. You ready?
I am ready. So let's go.
All right. Let's talk me through it.
Okay, so I think this is fairly straightforward. So when you ask the question, does when you suggest that a POMDP is generalized MDPs, what you're really saying is that if I have a true MDP, the POMDP can represent it basically without any painful extra effort. And so that means there has to be a case where there's really a direct and simple connection between the parameters of the POMDP and the parameters of the MDP. And you've already taken us a pretty far way there by pointing out the states of the states, the actions, the transitions, the transitions, and the rewards of the rewards. So what would the observables be? Well, if there's no uncertainty, there's no, confusion about what the underlying state is, then one way to capture that would be simply to point out that Z is S. There's a one-to-one correspondence from every state to every observable.
Okay, yeah, that's what I was looking for. I would say it a slightly different way, which is the notion that the vocabulary of things you can see, we might as well just reuse the vocabulary of the states because we're going to get to see them directly.
Right. So there's state 1, 2, 3, 4, 5, and 6. There's observables 1, 2, 3, 4, 5, and 6, and they match up in the obvious way.
Sure.
In other words, you can observe the states.
You can observe the states. Well, so far, all we've said is that the set of things you can observe is equal to the set of states. Now, we need to define the observation function to say that what we're really observing is the state.
Well, right. So that's the go. So those two things together will sort of give us what we want. So here's what I'm going to say. For any particular state, there is a particular Z, and no other Z matches that state, and no other state goes with any other Z. So I'm going to say that the probability of you seeing Z when you're in state S is 1 if S equals Z.
Which we could just shorten as 1 if and only if S equals Z.
Right, and that works because probabilities have to add up to 1.
Yeah, but there's additional constraints on this observation function that make it an observation function, or make it a probability distribution.
Yeah, so we could write that out as like, for all I, Z of I equals S of I or something.
Excellent. All right, so now that we get that idea, let's try to use it a little bit.
Okay, well, wait, is it, I mean, I think it's obvious, but is it obvious from here that MDPs do not generalize POMDPs?
Well, we would need to find some way of figuring out how to smoosh the observation function and the set of observables into the MDP itself. It doesn't seem so obvious that you can do that. Ultimately, we are going to do something a lot like that by expanding the state space significantly of the MDP. But I don't know. I mean, do you have something in particular in mind for that?
Actually, probably just that. I was just thinking that I could, if I could tag all the states with the observables and update the transition function accordingly, I could probably do it. But I guess that's not the same thing as saying an MDP generalizes a POMDP.
Agreed. Yeah, you can try to make an MDP out of the observations themselves, but it need not be Markov, right? It could be that you can see the same observation twice in a row when, in fact, you've actually changed the state and you changed the distribution over what futures are going to be like from there. So I guess that's a slightly subtle point, but the fact of the matter is it doesn't really go the other way unless we expand out our notion of state.
Okay, cool.
So here's a little tiny POMDP that I've thought about in the past that I think makes for good illustration. So we've got 4 underlying states, these 4 here, the 4 circles, and we've got 2 actions. The actions essentially move the agent left and right along this kind of hallway type thing, with some exceptions. So from the green state, any action just resets you randomly to one of the blue states. And otherwise, things move left and right. At the end of the hallways here, these 2 end states, if you try to go right when there's no more space to go, you just stick where you were. And if you try to go left when there's no more space to go, you stick where you were. And just to ground it the rest of the way out, actions that take you to the green state give you a reward of 1. So does that make some sense to you? Do you follow how this would go?
I do, and it's I just realized if I don't know which blue state I'm in, this is a scary, scary little problem to try to solve.
Good. So that was the thing I guess I neglected to point out. I'm showing the observations in this diagram with the colors. So let me just number the states just for ease of referring to them. We've got three states, 1, 2, 3, and 4. State 1 is blue. State 2 is blue. State 4 is blue. Based on the immediate observation alone, we don't know really where we are. And we could be a place that's to the right of the goal, so we should go left to get reward, or we could be a place that's to the left of the goal, which means we're going to have to go right to get reward. And so we're kind of in a tricky spot.
Yeah, this is unfortunate. You're trapped like a rat in a maze.
Oh, I see. Yeah, you're pointing out that to you, this looks like a rat drawing, but it really is not supposed to be a rat. This is not the nose. This is not the tail. It really is just transitions.
I think you doth protest too much.
So given that we think maybe we understand what the transitions and stuff do here, let's try to answer a question, and that'll at least kind of force us to think through how observations and actions and the states actually interact. So let's imagine, once upon a time, we took a left action, and we saw blue.
Mm-hmm.
Then we took a right action, and we saw blue. Then we took a left action, and now the question is, what's the probability that the color that we see next is blue versus green?
Okay. That sounds excruciatingly painful, but I probably can figure something out.
It starts to feel kind of like one of these liar paradoxes, right? Where you have to think about all the different ways that this might have been true and then figure out what's contradictory to what. But nonetheless, I think that you can sort of intuitively work through this, and so I think we should try. And then we'll develop some kind of math and a systematic way of doing this next.
Wait. I have one last question, I think, before I can do this.
Okay, sure.
So let me be right. You're talking about left and right here,
Mm-hmm.
but what about if I'm in state 3? Can I still go either left or right?
Okay, sorry. Yeah, so both left and right from to state 3 do the same thing, which is it resets us to 1, 2, or 4.
With equal probability.
Okay,
so now I think I've got it. So, I can go left or right in every state. It just so happens that in state 3, it doesn't quite do what you want it to do. All right, I think I'm ready to go. So, go.
We were going to work this through in front of everybody, but let's now work this through as the answer to the quiz. So the claim here is that let's say that for whatever reason, we know that we've started off in states 1, 2, or 3 with equal probability, a third, and we're definitely not starting off in state 4. Then we go left, see blue, go right, see blue, go left. What's the probability of what we see after that? This time, this actually does have an answer. And the question is whether or not it matches the answer that you gave or if it's something else.
Okay.
So how can we figure this out?
Well, instead of keeping track of the states that we could be in, we could keep track of the probability that we were in each of those states, because you're kind of representing the start as probabilities.
Great.
Now, the reason I thought we'd end up with 3/4 and 1/4, I thought that by writing down every time we were in some state, you wrote down the next state that we were likely to be into, and you kept track of all the different ways we could get to 1 and to 2 and to 3 and to 4, that we were actually keeping track of probabilities. But maybe I'm wrong. It's possible.
All right, so let's think that through. So after we've gone left and observed blue, what's the probability that we're now in state 1, 2, 3, or 4?
From here?
Yeah, we started off a third, 0.
Okay.
And now we want to know what happens after this first. We go left, we see blue.
So here's a question for you. So can we just assume we start out in state 1 and figure out where we would end up with what probabilities, and then multiply that by a third and do the same thing with 2 and the same thing with 3?
Yes.
Okay, good. So if we were in state 1 and we went left, we would definitely see blue.
Good.
And be in state 1 at that point.
Okay, so maybe what you're saying here is that we don't know where we are. We're kind of split. There's little ghosts of us, a third of us here, a third of us here, a third of us here. But the third of us that is here, when that one goes left and sees blue, it ends up in state 1.
Right.
All right, what about the ghost of us that's starting in state 2 here?
It also sees blue and will end up in state 1.
Okay. And what about the state 3 here?
Well, state 3, no matter what it does, will end up seeing blue for sure, but it will end up in 1, 2, or 4 with equal probability.
All right, so let's figure out what now our probability is after this has all happened. What's the probability that we're in state? Well, so let's do state 3 first.
State 3 is 0. It's not possible to get there.
That's right. All right, what about state 2? What is the probability that we're in state 2? If you just count these things, there's 1 out of 5. If we just look at it this way in terms of counting arrows, then we'd see, one of the arrows goes to 2 out of these 5, but it's not clear why that's justified. So.
Well, wait, it's completely clear why it's not justified. It's not justified because.
Okay, that's better.
Because you have 1/3 outside each of those arrows, and you can't ignore that. So, what's the probability we end up in 2? Well, If we were in state 3, then we had a 1/3 chance of ending up in 2, but we only had a 1/3 chance of being in state 3, so it's 1/9.
Excellent. And the same argument works through for 4, right?
Mm-hmm.
And so now, since the probabilities all have to add up to 1, we can deduce that it's 7/9. But is there a more direct way of getting that 7/9?
Yeah, it would be 1/3 times 1 plus 1/3 times 1 plus 1/3 times 1/3.
Good, right. So a third of the time we started in state 1, and all of those we'd end up in state 1. A third of the time we started in state 2, and all of those we end up in state 1. So that's 2/3 right there. And then a third of the time we started in state 3, and a third of those brought us to state 1. And if we add up all those pieces together, we get 7/9. It's like 6/9 and 1/9 is 7/9.
Right.
Great. This is weird, right? But this is kind of where we are after that first step. 7/9 of us are in state 1. 1/9 of us is in state 2. None of us is in state 3, and 1/9 of us is in state 4. And now what happens next?
Well, next I realize that we're almost certainly not going to end up in 3/4, 1/4. But who knows? Maybe we will. All right. So if I was in state 1 and I went right, then not only will I definitely see blue, but I will be in state 2.
Okay.
And there's no other option. If I was in state 2 and I went right, then I would be in state 3. And by the way, I would see green.
So something bad happens here, right? So we couldn't have been in state 2.
Right. So does that mean I get to recalculate what state I must have been in?
That is a good question. So yes. So it seems like in principle we should do that.
Well, let's finish seeing where else we couldn't end up before we do that. So if I were in state 3, which I'm not, it doesn't matter, so I couldn't end up anywhere.
Okay.
If I were in state 4 and I went right, then I would stay in state 4.
All right. So what's now our probability of being each of the possible states? And some of these are really easy. Like we know we're not in state 1, it just can't happen. And we know we're not in state 3, it just can't happen. But now it's sort of weird. Like it looks like we're in state 2 7/9 of the time, and state 4 1/9 of the time, but that can't be because it's not a probability.
Okay, so then what I would want to do, so using the reasoning I used before, I said, well, you should just take the probability you're in the state and the probability that you ended up in a state, right? So that's how I got that 1/3 times 1 plus 1/3 times 1 plus 1/3 times 1/3 to figure out the 7/9. Well, I want to do the same thing here, but I realize that the reason that worked before is because I had all the numbers adding up to 1. And here I don't actually have the numbers adding up to 1 anymore. So I'm going to say it's still 7/9 times 1 versus 1/9 times 1. But now I need to renormalize and get that to be an actual probability.
Okay. All right. So that is certainly one way to make things add up to 1 again, is renormalize them so that they add up to 1. Let's just do that. We have 7/9 and 1/9. That adds up to 8/9. So we need to divide everything by 8/9, which is like multiplying by 9/8. So the 9s cancel, and you get 7/8 and 1/8, which is what I wrote.
Right. So the only question is that right? I mean, so I think it's right, but that assumes, so why wouldn't that be right? Because, well, what if by learning that there's no way I could have been in state 2, that actually changes my original probabilities of what states I could have been in?
Yeah. So we should work this out more formally. But let's if assuming this is right, we should at least be able to write down what the probabilities are now. Right. So after step 2, we go right, we see blue, and now the question is, if we were to go left, what would we see?
That's pretty easy. So assuming our numbers are right, we know that we're not in state 1, so it doesn't matter. We could be in state 2. If we're in state 2 and we go left, then we're going to end up in state 1. We know we're not in state 3, and we could be in state 4, and if we go left, we will see green. We'll be in state 3. So those add up to 1 neatly. So that suggests that we will see green with probability 1/8.
Green with probability 1/8?
Yep.
And blue with probability 7/8? It's more likely that we'll see blue, but it's not impossible that we'll see green. Yeah, so that's the answer I was going for, and it's not, I mean, basically the weird step was we just at some point normalized because things didn't add up to 1. And that was the right thing to do, but it's not a great way of reasoning it out. We need to be a little bit more systematic and careful about that. But yeah, we didn't quite get to 3/4, 1/4. We got 7/8, 1/8.
Yeah, but that's the same thing for sufficiently large values of 1/8.
Yeah, well said.
Thanks.
So the next problem that we need to worry about is the problem of state estimation. And as we were just talking about a couple moments ago, we can make a POMDP into a kind of MDP by expanding out the state space. What we're going to do is consider what we call belief states. So the state that the decision maker is going to use in the context of a POMDP is going to be a belief state B. And what a belief state B gives you is that if you tell me a state like S, belief state B of S tells us the probability that we're actually in state S at the current moment of time.
So B is a sort of like a state. Well, it's a belief state. So it's like what we did in the last example. It's kind of a vector. It's a distribution over states.
Yes, exactly. It's a probability distribution over states. Yes, and that's going to encode for us. It's going to retain for us the information about the history that might be important for decision making.
Oh, okay. So it gets us all the way back to the beginning. Okay, so B of S then. So B is just a vector, and it's indexed by S, and S, instead of being an integer, is just a state.
Right.
Okay, that works. So it's a probability distribution. All right, that makes sense. Okay.
So now what we need to do is figure out how this belief state gets updated as we take actions in the world.
Okay.
So the way we're going to think about that is we're in some belief state, we choose an action, the world gives us back an observation, and we need now a new belief state to be formed from that.
Okay. So that's exactly parallel to we were in a state, we took an action, and we got into another state.
Right. So what we really are doing here is we're building up a notion of a belief MDP. So we're going to turn the POMDP into a kind of MDP, specifically the belief MDP, where the states of the belief MDP are probability distributions over states of the underlying MDP in the POMDP.
Okay, sounds good. So an aside, Michael, is if reward is a function of state, which it sometimes is, so you should be able to use that to update your belief state.
Right. So in what we're going to be talking about, the reward is essentially not observed.
Mm-hmm. But
of course, in reality, if you have a learner that's in some environment and it's making observations and getting some reward back, it can actually, if it knows something about how that reward is being generated, it can use that as a kind of observation. And so we can essentially assume that the observation has whatever information might be in the reward in it.
Right. So, in fact, the observation is whatever sub-features you get to see plus the reward.
Yeah, I've seen some people write it this way, where you say that the reward is actually something about the observable. All the reward you get is extracted from what you observe. And so anything that you model in the POMDP as being reward relevant has to actually show up in the observation.
All right. That seems reasonable.
Right. Otherwise, you kind of can't learn if you can't observe it.
Right. That makes perfect sense.
All right. So what we need to do is derive how we get this probability distribution over states, B prime, from the old belief state, the action, the observation, and whatever quantities in the POMDP that we have. So what we need to figure out is, in this new belief state, after we've taken action A and seen observation Z, what is the probability that we're in state S prime? And so we're going to have to do some kind of probabilistic, I guess, inference or derivation to work that out.
Sure. We ought to be able to do that, right? Because we have all the quantities that we need in the POMDP, I think.
Well, that's the hope. So we want the probability of the next state, given that we're in a belief state, took an action, and made an observation. So can we manipulate this expression using the laws of probability to make sense out of it?
Sure.
That's a good answer. So what would be a piece of information that, if we knew it, would make it relatively straightforward to figure out, what new state we were in?
Well, if we knew which state we were in before, since we have a transition model, we know which states are likely to be in next.
Yeah. Okay. Well, let's just write that. That's a really good start. So what we're saying is, let's break things down by the possible state that we started in, and what we want to know, and we're going to weight things by, well, what's the probability that that's the state we started in, given BAZ. Then, given that, what's the probability of the next state, given that state? So this is going to help us break things down successfully. So let's see if we can do that. So what do we know about the probability of being in a state, given a belief state that we took an action and we made some observation? So I think that the thing to point out here is that the observation that we saw is generated by the state that we ended up in. And so we're actually trying to figure out what state we were in based on the observation we got, when in fact the generative model goes the other way. So this is a prime situation to try to use Bayes' rule.
Prime.
It's an S prime situation for using Bayes' rule. So that gives us the probability of making an observation given the state that we're in, or that we arrived in, S prime, and carrying over the A and the S, and the probability that that's the state we ended in, given A and S, divided by the normalization factor, the probability of the observation given A and S.
Right.
All right, so now we're getting really close to quantities that we recognize. In particular, the probability of an observation given the state that we just landed in is independent of the action and the state that we just took.
Mm-hmm.
So this is going to be the observation function. This right here is the transition function, the probability of landing in some state S prime given that we were in state S and took action A. And then this is just going to be a normalization factor at the bottom.
Right.
So substituting those quantities in and rewriting out this normalization factor as basically the numerator divided by the sum of all the possible next states S prime, we get one component of the new belief state B prime. If we apply the same idea over all possible states S prime, then we get a probability distribution over all the states that represents the likelihood of being in those states given that we were in belief state B, took action A, and made observation Z.
Oh, so that's intuitively obvious even to the most casual observer. But more importantly, it just uses all the quantities we already had.
It does. It seems like sort of like when a TV series is over and they bring all the characters back for one last show. It's like, we got the B back and the O back and the Z back. Everybody's friends again.
And it spells bot.
And it spells bot. So my point is that these quantities can be easily calculated this quantity, this B prime S prime, can be easily calculated from quantities that we have lying around because we have the model of the POMDP and we know what the previous belief state is and we know what action we just took and what observation we made. And so all this can be updated. And so we can keep track of kind of this notion of where we are, this belief state notion of the belief MDP.
I like it.
Cool. All right. So this doesn't actually tell us how to do decision making because what we've done actually is we turned a POMDP into an MDP that, by the way, has an infinite number of states. So we have a number of algorithms that we can run, like linear programming or policy iteration or value iteration, and they all at best grow polynomial in the number of states, so it's polynomial in infinity. So
it's a constant.
Yeah, no. It's bigger than any constant. So this is problematic. We can't just take this MDP now that we've defined it and just solve it using our existing algorithms. We're going to have to be a little bit more careful. And so I want to step through the algorithmic process for how you can actually do that. It's kind of nice, I think.
Okay. I mean, I can't wait to see how you make infinity, so let's do it.
So the trick for doing algorithms like value iteration in infinite state space, like what you get from the belief MDP, is going to come only by looking really, really, really carefully at the infinite case and then showing that we can re-represent it in a finite way. So what we're going to do now is actually step through what value iteration would look like in POMDPs, and then piece by piece we're going to convert that to something that actually can be computed. So at first it's going to be math, and then it's going to be an algorithm. So here's value iteration written out. And it's in POMDPs, but sort of doesn't really matter yet. We're going to define the value function at step 0 to be, as a function of the belief to just be 0 everywhere. And then we'll say for t greater than 0, the value function for time step t as a function of the belief state B is going to be the max over all actions, the reward for taking that action in the context of that belief state, plus the discounted expected value of where we end up, right? So what we're going to observe is an observation Z, and so let's sum over all the possible observations, the probability that we make that observation times the value function at the previous time step for the resulting belief state B prime, which is what we get by doing what we talked about on the previous slide, which we'll call the state estimation for BAZ.
All right, that seems reasonable.
Yeah.
I mean, other than the fact that R is not a function of B and A, that just means the reward you actually got.
Right. So let's what is this like? What is the reward for being in belief state B given that we take action A, how can we re-represent that in terms of quantities that we're more familiar with?
By unrolling probabilities or something the same way we did last time?
Yeah, and in particular, all we have to do is say, well, we would get the reward for state S if we were in state S. So let's just sum over all states, the probability we're actually in that state, the reward that we would get from that state. And of course, this is just the belief state for state S. So this is really just the dot product of the belief state with kind of a vector that you could make out of the rewards for a given action.
So it really is just the average reward you would expect given the belief state.
Exactly.
Okay.
And so again, now that we've got that out of the way, the scary thing here is this function v, this value function, is defined over an infinite set of belief states, these vectors of probabilities over states. So again, we're not going to let that scare us quite yet, but it is something that we have to keep in mind. Otherwise, we could just implement this directly. All we would need is a loop that would say, for all belief states, do this update. It's just that there's an infinite number of them, so that would not terminate.
Yeah, but you could write it in really just a few lines of code.
Yes, you could write an infinite loop in very few lines of code.
It's beautiful, really.
This is how we're going to jump from the infinite to the finite, to the finite. Is we're going to make a claim, and the claim goes like this: that for all t, the value function at time steps t over all belief states b. Wait, this is right. So this is over the infinite set of possible belief states, can be written in a finite way. In particular, the maximum over some set of vectors, gamma sub t, that we're going to have to deal with later. But the point is that it's a finite set of vectors. The maximum of the dot product of the vectors in that set with the belief state.
Okay.
Where a dot product is really just the sum over all the states, the weighted probability being in that state times this alpha of S. So this kind of function is sometimes called piecewise linear and convex. And the reason is that if we think about belief space as being, well, let's just do a really simple one, like the space of probability distributions over just the two possible states. So we have some probability between 0 and 1, and if we are probability 1 represents we're totally definitely in state S1. Otherwise, if the probability 0, we're totally definitely in state S0, and in between, we're in between. There's some probability of S0, some probability of S1. Halfway in between would be half of each. Okay. So what functions of this kind have in common is that each of these alpha times b is a linear function of the belief state. All right. So each of the alphas in this set, capital gamma sub t, is some linear function of the belief state. And what we're going to do is we have a whole bunch of them. At any given belief state b, what we're doing is we're taking the maximum value of all these possible linear functions. So at the end of the day, the actual function that we've represented is this upper surface of these linear functions, each of which is defined in this set, capital gamma. Does that make some sense?
Sure. It makes me think of something we did in the last class.
What was that?
Well, when we did the game theory stuff. Remember that?
Yeah, so maximums over linear functions comes up in game theory as well. Yeah, it's a good point.
And they end up looking very piecewise linear.
Yep, and convex, right? This is sort of open upwards to the top. And that's because of the max, and the piecewise linear is because it's a finite set of linear functions. So it's probably not obvious why this would be true, but this is the thing that we're claiming, and I want to at least make it clear what we're claiming. The claim is that any value function at any given step of value iteration can be represented finitely as just a maximum over a bunch of linear functions. Each linear function can handle an infinite number of inputs, right? And that's not so surprising if linear functions can do that. Mm-hmm. But what's cool is we don't actually have to represent the value for each possible belief state B. Instead, we just throw all these linear functions into a bag, gamma sub t, and then when we want to know the value for a given belief state B, we compute all the linear function values and just take whichever one is the highest at that point.
Okay. I mean, I guess that makes sense in the abstract. I guess the only thing that I don't yet get is exactly where gamma comes from.
Yes, that's what we have to step through. And that is not at all obvious, I think, but it is very elegant that it all works out. And this was originally shown by a fellow named Sondic. And, once you see it, it's maybe not so hard to see, but I don't know how he got here in the first place. It's to me, it's not all readily apparent. But once you see things this way, it gives you a very powerful way to work with these infinite-sized state spaces. You just have to take operations on bags of vectors. And so it ends up all being finite. So what we're going to do actually is a proof by induction. We're going to show that the base case is that we can represent the value function at time step 0 using a finite set of vectors. And that if we can represent the value function for some state t minus 1 with a finite set of vectors, then we can construct a finite set of vectors for representing the value function at t. So let's start off with the base case. So this is going to be a quiz because it's really, often base cases are not so hard. This base case is not so hard. Here's what we need to do. We need to show that there exists a set of vectors, gamma sub 0, such that we can actually represent the 0th step of value iteration function over all possible belief states as the max over alpha in the set that we're about to define as the dot product between that vector alpha and the belief state B. So what you need to do is figure out what does this bag of vectors look like that has this wonderful property of representing the 0th value function.
All right, I got it.
So let me give a hint.
Okay.
Can you remind everybody what is V0 of B?
0.
Yes. So what we're trying to do is figure out a set of vectors such that you get that.
Okay, I can do that.
Let's just kind of work this through.
Okay, well, actually, I think there is an easy answer.
Okay.
I guess we'll discover whether it is the answer. As you pointed out before, there's actually a big hint. We know that the value function is supposed to be 0 everywhere.
Right.
And we know that the values for B, of course, are whatever. They all sum to 1, and they're between 0 and 1, and, the usual thing, their probabilities.
Yeah, it's like a vector, and the dimensionality of that vector is the number of states in the MDP. Mm-hmm.
Right, and the sum of all of them has to be 1, and blah, blah, they're non-negative. So the easiest way to get something times something to equal to 0 is to have one of those somethings be 0.
Good, okay.
So I would say that the gamma is, 0. It's the 0 vector.
The 0 vector, where the dimensionality of this vector, again, is the size of the state space.
Right, so I would just write 0, a capital 0. Right, that's how you usually write those things.
How do you make a 0 capital?
You make it bold, or you put a little arrow, a little vector symbol on top of it. You're drawing the Green Lantern symbol there, but okay.
It sort of happened. I didn't mean for it to happen.
Right. So the answer is 0 because 0 times something is 0.
Right. We only need one vector in that set. Whatever belief state we take the dot product with that 0 vector with is going to come out with 0. The maximum over that one vector is going to be that 0 value. This is just going to spit out 0 everywhere.
Yeah.
So do you agree that was kind of easy?
That's pretty straightforward once you remember that we set the value to be equal to 0. Did we do that on purpose?
Yes. There's another thing that you could do that actually makes things work nicely also, is to say that the value at time step 0 is whatever the immediate rewards are. That turns out to be okay as well.
Oh, and then what would the gamma need to be? 1?
No, it ends up being the reward vector.
Oh, right, because then you add them all. Yeah, that makes sense. Okay, fair enough.
And as you might expect, and in fact, as you told me offline that you did expect, what we're going to do is VT is defined using the Bellman update, right? The Bellman equation in terms of VT minus 1. So what we're going to do is structure things around that Bellman equation. So what I've done here is broken up the Bellman equation into kind of a series of steps. VT of B is the max over actions of something. What is that something? The something is the sum over all observations of something else. And what is that something else? That turns out to be the sum over all states of the reward function for that state given that action times the belief state, and then normalized by the number of observations, plus the discounted expected value of the next state. The expectation comes over the observation, Z, and then the value of the next state is VT minus 1 of the state estimation of BAZ. All right, so this is really just the Bellman equation, but I kind of unrolled it, I guess, or kind of untelescoped it, so that each of these operations is going to be easier to build out of vectors.
Okay, so that the sum of the S is just for the thing on the left side of the plus.
Yes.
Right, because it's just the reward.
Right, and what's going to happen is this side is also going to have a sum over S in it, weighted by a B of S. Mm-hmm. And that's going to allow us to actually think about this whole thing as a dot product of the belief state with some kind of messy vector.
Okay, I like messy vectors.
So here's what we're going to do. First thing we're going to note is that if each of these things could be represented by a bag of vectors, max over a bag of vectors, then all the other ones could also be represented as max over a bag of vectors. So the easiest one is the very first one. The first one says that the value function at time step t is the max over actions of some other kind of thing. If this is represented as the max of a bunch of dot products over belief states, then think about what happens if you just take all the vectors for all the different actions and throw them into one big bag. So imagine that we've got one set of vectors that represents a value function, And then we have another set of vectors. This is for one particular action. Then we have a set of vectors that represent the value function for a different action, call it A2. So the thing to note is that the max over the max over the bag of vectors, this upper surface here, is actually the right thing. That if A1 gives the highest answer in one case, then we get that. If A2 gives a higher answer in another case, we get that. We can just pool all the vectors together. So this is just a union over all actions of the bag of vectors for each of those actions. This is a way of writing max as an operation over sets of vectors.
Sure, I believe that. That all makes sense.
The next piece is that the value function for an action A at time step t for belief state B, we said that it was the sum over observations of some particular vector that we get for that observation. If these can be represented using bags of vectors, then this sum over observations can also be represented using operations over bags of vectors. And in particular, what we end up having to do is take those bags of vectors and compute what I like to call a cross sum. It's basically the sum where we choose for each of the observations, we choose a vector, and then we add those vectors together. It ends up producing the same effect as this sum. So what we're doing here is now, given a set of vectors, one set for each action observation pair, we're going to create a bag of vectors just for an action by taking this sort of cross sum, summing out all the different observations. Because that's really what we're doing. We're summing out over the observations.
So that's just really a fancy way of writing what you just wrote.
Yeah, but again, it's letting us go from this function v, which is over an infinite state space B, to just a finite set of vectors. We have a set of vectors, and we generate from that a new finite set of vectors. So in this case, the number of vectors, this first step, the number of vectors is the sum of the size of the number of vectors in all the sets, gamma AT. Here, we're actually multiplying. So it's the product of the sizes of all these sets, which is finite, but it could get actually quite big.
I guess now that you say that, you should say out loud that you're making assumptions that everything else is finite too, like the number of actions and things like that.
Sure. That was already built into the definition of MDPs, the way we were talking about them.
Fair enough.
But yeah, it's probably worth repeating that certainly if the number of actions is infinite, then this is problematic. This union is problematic. And if the number of observations is infinite, then this cross sum is problematic. So we're finite state space, finite action space, finite observation space.
Okay, so I'm getting the idea. Basically that if you can start out with something finite, at every step of the way, you might grow, but you're never going to grow an infinite amount in a single step. And therefore, so long as the number of steps is finite or bounded or some word like that, you will maintain a finite number of things in your bag. That's kind of what you're doing step by step. Okay.
That's what we're going. And if it feels like there could be a lot of vectors, this is true. It actually can grow doubly exponentially with t, the number of iterations of value iteration we're doing. But for now, we're pretending that's not a problem.
Yeah, I mean, look, exponential is bad unless you're comparing it to infinite.
That's right. That's right. We set things up so that exponential is actually awesome.
Yeah, because it's finite. So what's the last one?
So what we're going to do in the last step, and I probably shouldn't go through all the grungy details, though all the pieces that you need for this have been in stuff that I've said. But what we're trying to do now is represent this value function VAZ of t applied to the belief state B, and we said that was going to be basically a dot product of the belief state with some kind of reward vector for the current action, plus a weighted version of the value function for the previous time step. So it's going to be helpful to actually take the value function at the previous time step and write it out more explicitly. So this is basically just expanding on the definition of the state estimator that we did in the previous slide.
Mm-hmm.
We're going to say that the value, according to the t-1 time step value function, for the belief state that we get from taking action A and making observation Z from belief state B, we can write this out as the maximum over all vectors in that set of the dot product of that vector with the resulting belief state, which we had previously derived to have this form. Okay, the observation function times the transition function times the belief state, and then normalized. And this normalization factor is the probability of making the observation Z given that we're in belief state B and action A. This is a highly nonlinear function, but this is the awesome part. Ready? Since we're going to ultimately multiply this value function times the probability that Z is the actual observation, in other words, probability of Z given B comma A, this and this end up canceling. And what we're left with is an actual linear transformation. So this weird divide by thing that actually makes things really yucky cancels itself out. So convenient.
Just like life.
Not usually. But math sometimes does this for us. And so at the end of the day, we end up with a quantity that is a dot product with the belief state and another quantity that is a dot product with the belief state. We can factor out the belief state, and what it leaves us with is a giant vector, one for each combination of observation, action, and which gamma is going to be the maximum at that observation. So we actually have to take the product of the number of vectors that was in the t-1 set raised to the number of observations times the number of actions. And that's going to be the maximum size of the set that we get for representing the t-step value function. So, like you said, could blow up, but still finite. Can't blow up to be infinite if it started out as finite.
Nice. So that feels like a proof by induction to me.
Great. Okay. And so you wouldn't want to actually do this. There is code in Burlap for doing a lot of these processes. There's also my collaborator Tony Cassandra created a program called POMDP Solve that you can download that actually that does all these calculations carefully and on your behalf. So I didn't really want to get this to the point where you could actually necessarily code all this up, just to believe that it's code upable and you can use an existing implementation if you want to actually run it.
It's very mathematical of you.
So there's one more step before we can get something that you can actually implement it this way, but this is guaranteed to be exponential because you're actually combining all these things together. There's one step that we can do that if it's the case that the Q functions have a small representation, then the algorithm will run quickly.
All right.
Here, it could be that the Q functions are actually very, very big. Oh, in case it's not obvious, the Q functions are represented right there.
Oh, yeah.
I called it VA sub t, but that's really the Q function.
I like it.
To explain how we can actually keep this from getting out of hand if it doesn't need to be, we're going to look at one special operation. And let me draw a picture of it first, and then we'll talk about it more mathematically. All right, so do you see what I drew here?
A web?
Yeah, it doesn't look so great, does it? So this is intended to be a piecewise linear convex function. So basically a value function. And remember that what we end up doing is over belief space, the black line here, we're going to be taking the max over all these linear functions. So we get this upper surface.
Wait, I see. You can get rid of any of the vectors that don't ever participate in the max because they don't matter.
Yeah, and so that's going to keep our vector sets potentially from blowing up if they don't need to. So in this particular case, I drew, 1, 2, 3, 4, 5 vectors, but only 3 of them are really needed to represent the function. This one's not needed, and this one's not needed. Mm-hmm. So we can define a computational operation that we call Purge that takes a bag of vectors and shrinks it down, purges out any of the vectors that aren't really needed to represent the upper surface, the piecewise linear convex function.
Wait, how computationally complicated is it to do that?
That's a good question.
Thank you.
So how computationally complicated is it?
It's at least linear.
It's at least linear, yeah. And so there's some quick tests that you can do. So let's look at this vector first, this vector number 1 here. If you look, what you can see is that over belief space, this 0, 1 zone here, there's another vector, specifically this one, call it vector 2, that always dominates it. It is always the case that you can do better by taking vector 2 instead of vector 1. So if there's a vector that is dominated by another vector, you can totally throw it out.
Which you ought to be able to figure out by doing something cute, like multiplying them together or taking their cosine at their angle. There's something you ought to be able to do to figure that out.
Actually, all you have to do is check the corners.
If it's bigger on both 0 and 1, then it must be bigger the whole way through.
Well, in particular, let's say we have 2 vectors like this, with components alpha 1, alpha 2, alpha 3, and this is this vector, and the other vector is represented by alpha 1 prime, alpha 2 prime, alpha 3 prime. If it's the case that alpha 1 is bigger than alpha 1 prime, and alpha 2 is bigger than alpha 2 prime, and alpha 3 is bigger than alpha 3 prime, then this vector is not needed, right? No matter what belief state you stick in, you're going to get a higher value or out by using this vector than that one.
Does it have to be strictly dominated, or can it just be dominated? So if one is greater than or equal to the other, you can get rid of the one that is less than or equal to, right?
Yes.
All right, that's neat.
Yeah, there's some subtleties to doing this consistently. In my dissertation, I talk about how you can use a lexicographic ordering of the vectors to make sure that you only keep things that really are going to be needed someplace. But that is a subtlety that I don't think is very important for this. This dominated check is actually really easy to do, and it's very fast, but unfortunately it's not sufficient. So let's look at this vector. We'll call it number 3. This one is better than each of the other vectors at some point along the way. But the union of the other vectors, the union of these 3 vectors, dominates it. So showing that is actually considerably more difficult. Like knowing that 3 doesn't matter, isn't needed, because over here it's dominated by this vector, over here it's dominated by this vector, and over here it's dominated by that vector.
Wait, what you said isn't true. 3 is dominated by the one that first does the max all the way through.
You mean this one, 4?
Yeah.
Yes, that is a good point. All right, that sounds like a quiz.
Okay.
All right, so what we've got now is a piecewise linear convex function, represented in this case by a vector that goes from P1 to Q4 and P4 to Q1. And now what I'd like you to do is add a vector to this set that has 2 properties. One, it is purgeable in the sense that it actually isn't above the maximum at any point, but it isn't dominated. There isn't one or the other of these vectors isn't greater than or equal to it everywhere. So it needs to be a vector that's not dominated by either of these vectors, but doesn't actually come up above the max of these vectors.
Okay. I think I can do that.
Cool. This will kind of help you thinking about these kinds of linear functions. Really, they end up being used in extremely high dimensions, which can be hard to work with. But for this small dimension one, low dimension one, I think it's not so bad.
I think this one is actually pretty straightforward. Okay, so I think the students will be able to get this. So go. Okay, so I think this one's actually fairly straightforward because of the way you've drawn it.
This is ultimately multiple choice, and there's only 16 possible things. So we could just go through all of them.
We could. And let's start with, just coincidentally, how about P3 to Q3?
That doesn't seem like much of a coincidence. All right, so if we draw this vector from P3 to Q3, then what properties does that vector have? Does it participate in the max?
It never once participates in the max, and yet it crosses both of the lines and therefore is not dominated by either one of them.
Yeah.
Oh, man, we got really lucky there.
I guess that's one way to think about it. But, I mean, it's sort of worth considering, like why not...
We'll do all the parallel ones. Do P2 to Q2.
P2 to Q2. Well, PQ to Q2 ends up being part of the max, so that's not good.
That's right. As would P1 to Q1.
P1 to Q1. Yes, definitely.
In fact, it is the max.
Yeah, it makes everybody else irrelevant.
Mm-hmm. And P4 to Q4 never participates in the max, but is dominated by both of them depending upon whether equal to counts as dominated.
Yeah, so let's draw this one in, the P4 to Q2. So this vector is underneath this vector always, right? So we could just check this one vector to know that this one's not needed.
Right.
And so that's not what we're looking for. It is dominated by this other vector.
And that would also be true for P2 to Q4 with the other vector. And then anything that goes down from there. So if P4 to Q2 is dominated by P4 to Q1, then so would P4 to Q3 and P4 to Q4.
All right, so this is the unique answer to this question.
Yes.
And so one thing that I think is actually worth pointing out while we have this particular picture is when you're dealing with these kinds of alpha vectors, these linear functions over belief space, this P1, P2, P3, P4, Q1, Q2, Q, you can think of those as actually being the components of the vector, because the corners of belief space are the places where one component is 1 and all the other ones are 0. So the actual vector itself has exactly this form, that this vector, P1 to Q4, actually has a value of P1 in the first position and a value of Q4 in the second position.
Neat. And so that makes it more straightforward to kind of do the munging and the whatever. So you didn't actually give me a final answer of what the computational complexity of doing this purging would be.
Yes, this was just an aside. So to actually do this kind of purging involves solving a linear program.
So it's big O of a linear program.
Yeah, that's right. That's right. So it's basically polynomial with respect to the time it takes to solve linear programs, which is polynomial, but it can be kind of expensive. But it still does. What we have found is that it still does help to do all this purging, run all these linear programs to get the redundant vectors out, because if you leave them around, they just cause things to blow up.
Right. And since you keep purging things, even though you're going to run a linear program again, you're running a linear program over fewer things.
Right. And so this sort of interspersing purges among all the different vector operations actually tends to keep things, if it's going to be small, it tends to keep things small.
Okay, this makes perfect sense to me.
Do you want to actually see the linear program?
Sure.
I did not expect you to say yes to that.
I didn't. I said sure.
All right, we'll do that next time. So now that we have an idea of what POMDPs are about, maybe we should talk a little bit about what it might mean to do reinforcement learning in them. Because we basically talked about planning. If we have a model of the POMDP, we can run some calculations. We can run value iteration to get a way of deciding what to do. Actually, did I say that? I think I did not say that. I think what I said is how you get a value function. Is it clear how you would use a value function to get a policy?
In the same way you would for an MDP, right? Yes? No? That's not true?
Yeah, that's right. If you have the model, then you can use one step look ahead with the value function to figure out what the optimal action is in any given belief state. Once we've run value iteration and gotten an approximation of the optimal value function. Oh, and what about that? Value iteration doesn't actually necessarily converge.
It doesn't? You didn't tell me that.
I did, actually, when we were doing in lesson AAA.
Lesson AAA?
Yeah, the advanced algorithm analysis. What we said there is that value iteration converges in the limit to the right value function, but after any finite number of steps, it need not have the optimal value function. But it will, after some finite number of steps, have the optimal policy. That's not going to be true in the POMDP case because there's an infinite number of states.
Oh, I see.
But it is going to be the case that we get an arbitrarily good approximation after some finite number of iterations.
Wait, arbitrarily good approximation of what?
Of the optimal value function.
Wait, but not necessarily the optimal policy?
Yeah, if you do one-step backups or one-step look ahead with a near optimal value function, you'll get a near optimal policy.
Okay, so that's nearly good.
Now that we've talked about planning in POMDPs, we should talk about reinforcement learning in POMDPs. Charles, what's the difference between planning and reinforcement learning?
Well, in planning, you know everything, and in reinforcement learning, you don't know everything, and you have to explore and exploit and do all that other stuff in order to find things out. Like you don't know the model necessarily, and that makes the problem harder. So what you're telling me is reinforcement learning is harder than planning in the way you're using the words, and POMDPs are more difficult to deal with than MDPs. So reinforcement learning in POMDPs should be like, is that additive, multiplicative?
So reinforcement learning in POMDPs is hard, like super hard. Actually, planning in POMDPs is formally undecidable in the sense that...
Undecidable?
Yeah. If I give you a POMDP and ask, is this the optimal first action to take from this belief state? If you could solve that problem, you could solve the halting problem.
Holy cow. Wait a minute. That has profound implications.
No, it doesn't.
Yes, it does, because we're human beings running around in the world. We're living in a POMDP because we can't know everything. So you're telling me that even if I could relive life an infinite number of times, I still don't know what the right thing to do is. You're saying that life is unknowable. It's undecidable. You can never know what to do. That's profound. Wow. I need a moment. So basically, planning is hard, so I assume reinforcement learning is also hard.
So the results that we have for reinforcement learning in POMDPs are more empirical and algorithmic results. They're not really formal results. But it's still something that people try to do sometimes, right? If you have some kind of robotic system or agent system that's trying to figure out what to do, and the world that it's in is partially observable, then you have to do something like this.
Yeah, solve the halting problem.
Well, no. Getting the exact optimal answer is undecidable.
Well, is it decidable that you can get near optimal?
Yes.
Oh, okay. Well, then I feel better. Why don't you stop depressing me and tell me what to do so that I can sort of feel better about this whole approach?
Sure, no problem. All right, I'm going to ask you what to do. So in particular, do you remember we had kind of two main flavors of reinforcement learning algorithms for MDPs? Do you remember what those were?
There's value iteration and policy iteration, right?
Yeah, those are planning algorithms. But for reinforcement learning in an MDP, the two main branches, model-based RL and model-free RL.
Oh, yeah, sure. Right. Well, that was obvious.
And do you remember the distinction between them?
Well, one used a model and one didn't.
One learned a model and one didn't.
Okay, well, the same thing. You can't use a model if you don't learn it if you didn't know it.
That's true. That's very well said.
So you learn a model and then you use it versus don't bother to learn a model and just do it. I think the little quip was, the world is your model.
Whose quip was that?
Probably Rod Brooks.
All right, so we can actually use this same kind of distinction, this model-based RL and model-free-based RL, or model-free RL, in the POMDP setting, where in model-based RL, you actually try to learn the POMDP, and then you plan in it. And in model-free RL, we try to map observations to actions. And we do that iteratively over time. So we don't actually build the model, but we do try to figure out, okay, when I see this is a good thing to do.
Well, can I ask you a question while we're here before you jump in? So one of the things that, we learned in AI class 150 years ago is that if you don't know what's going on, you can often figure out what's going on by taking specific actions that guarantee you end up in some state that you actually know.
Sure.
So even if you're blind and you're trying to get to a particular place in the room, you could do stuff like, well, I'm just going to go left for 15 minutes, and then I know no matter what happens, I'm going to be against the left wall. Then I know where I am.
Yes.
And then I can do things. Do either of these methods do the equivalent of that or an analog of that?
Either could, in fact.
Oh, okay. Well, that's good.
Again, the the guarantees on whether things actually work in this space are non-existent. So it's not the case that we can always say, oh yeah, it's always going to do the right thing. It's going to figure out the simplest way of getting to a known state and then behave from there. But yeah, I mean, I've seen both these kinds of algorithms do that kind of thing.
Okay, good. Well, that's promising.
For learning a POMDP itself, it actually is really helpful to think about the relationship between POMDPs and other kinds of Markov models. So I've made a little 2x2 chart that I like to think about sometimes, and we're going to fill it in. The 2x2 are, you can have a Markov chain or Markov structure that is controlled or uncontrolled, and you can have the controller be able to observe the state or only partially observe the state. And for each of these four things, we get four different models that we've talked about. Not necessarily in this class.
Okay.
But it's helpful to think about the relationships between them. So do you think maybe we could fill this in?
Well, sure. We can give it a try.
Okay.
So I guess what I'll suggest to the students is they go and they spend a couple of months reading everything so that they can answer this question and then come back. All right? Can you do that? All right, go.
Wait. I mean, not to give away the farm or anything, but couldn't they just listen to the answer video and then go back? It seems a lot faster.
Well, but you can't get to the answer video without first, clicking stuff and trying things.
Oh, yeah. All right. Sorry.
Yeah. All right. It's fine. It's okay. Well, in any case, I think my previous advice stands. So go forth.
You ready to give this a shot? Let's start with the easiest one.
Which one is that?
Let's say, what do you call a model that's partially observed and controlled?
Oh, well, we've been talking about that. That's a POMDP.
Yeah.
Or a PO-MDP.
PO-MDP.
As opposed to a rich MDP.
Rich MDP, yeah. If you actually can observe the state at all times and it's still controlled,
then it's a FOMDP, or fully observable Markov decision process, which we sometimes just call MDP.
Yeah, which is just an MDP.
Right. It's like the difference between an assistant professor, an associate professor, and a professor.
Mm.
Yeah. You start dropping prefixes as you become fully observable. Right.
You become fully observable. Yeah, okay.
All right.
Like full professor, you can just say professor. Fully observable Markov decision process, you can just call Markov decision. Oh, I guess it's the word full, really, that you can always get rid of.
Right. You can always get rid of full, because that went without saying. All right. Okay. So we know what an MDP and a POMDP is.
Now, the uncontrolled version is what we haven't really been talking about in this particular course. But I kind of gave it away in the question. If you have something that's observed and uncontrolled, you basically just have, it's jumping around between a bunch of discrete states.
Right. And we talked about that a little bit when we talked about passive RL. But this is really just a Markov chain, which are words you actually used earlier.
Yeah. So MC.
Yeah. MC-MDP is my favorite.
What is this?
All right. So then the last one.
This is kind of the payoff. So you could go with POMC.
Yeah, it could be a POMC or POMKey, but I actually think we talked about this in our last class.
Yes.
Yes, and in particular, in our last class, we said we weren't going to talk about it because
really? I thought we talked about it.
Well, we talked about not talking about it because it's a hidden Markov model, or HMM.
HMM, right. And so wait, so we really didn't talk about them? Do we know how to learn an HMM? Because here's where I was going with this. My goal was if we could remember the relationship between an HMM and a POMDP, and we can remember how to learn an HMM, we can use that same idea to create an algorithm for learning POMDPs.
Yeah, I think that's fine.
But do we know how to learn HMMs?
Somebody does. I mean, but I'm pretty sure we didn't talk about it in the last class. But that's okay. We'll just have Chris or somebody do a whole thing on HMMs, and then you can just pretend that people already know about it.
Well, okay, no, but I'm pretty sure we did talk about this idea.
Yes, we did talk about expectation maximization, and I believe you did mention that it could be used to solve HMMs.
To learn HMMs?
Yes, to learn HMMs, which is like solving them.
So, okay, just a quick refresher on EM then. So in EM, we actually go back and forth between two quantities that we don't know. We don't know the model, the hypothesis, the actual thing we're trying to build up. And we don't know the expected value of the hidden variables, given the data that we're seeing. But we can actually use each of those to improve the other. So we start off with a guess of the model. We use that to estimate the expected value of the hidden variables given that guess. Then once we have those expected values, we can actually use that to re-estimate the model, find the maximum likelihood model, and that gives us a new model that we can then use to compute the expected value of the hidden variables, and we just go tick-tock back and forth like that.
Right, and so my recollection from the last class is that we did this with Gaussians. So we had a bunch of Gaussians and a bunch of data, and we didn't know which of the Gaussians each data point came from. So we started out with a model of what the Gaussians, which was their mean. So we had a bunch of means of the Gaussians. That was our model. And then given the model, that is the means of the Gaussians, we figured out the probability of each point belonging to each of those Gaussians, and that was the hidden variable. The hidden variable was which Gaussian each of the data points belonged to. So we computed an expectation over those. And then once we had the sort of probability of each point belonging to each Gaussian, we were able to use that to recompute the means of the Gaussian. And back and forth and forth and back and back and forth and forth and back. And eventually you converge to proper means for your Gaussians.
That was the use of EM that we talked about. You can do a similar thing with HMMs, where you're actually, the hidden variables in this case are what state was the system in at a given moment in time in the observed data. And it turns out you can do essentially the same thing with POMDPs, that where you imagine that you've got some kind of hidden state model. You use your observations of, oh, I took this action, I made this observation, I took this action, I made this observation, to estimate the hidden variables, which state was the POMDP in, or the underlying MDP in at each moment in time, and then we use that to re-estimate the model of the POMDP. So that's actually all we need to say about that, or all we can say about that. Lonnie Chrisman was the first person to point this out in the 90s, that, hey, we can learn our POMDP the same way we learn MDPs.
And is that fast or not slow?
Yes, that is fast and not slow. No, that is fast. No, that is slow. No, well, so the fact of the matter is there's some interesting results that seem to indicate that there's some POMDPs that are really easy to learn and it doesn't matter which algorithm you use. And there's other POMDPs that seem to be really hard to learn and it doesn't seem to matter which algorithm you use. There is no guarantee that we'll be able to learn a good POMDP. It turns out that learning a good HMM is already known to be very hard. So adding actions to it doesn't actually make it any easier in the worst case. That was all we were going to say about model-based reinforcement learning in POMDPs, and now we're going to talk a little bit about model-free reinforcement learning in POMDPs.
Okay.
And in particular, we're going to focus on memoryless policies. And what I'd like to show, actually, is not so much about learning, but more about planning. So here's a little POMDP. This is a POMDP that has 4 underlying states, 2 observations. There's this sort of clear blue thing, and there's the green thing.
Mm-hmm.
2 actions, black and red. Black takes you to the right, and red takes you to the left, back around the other way. And the way that this is set up, it's kind of like I think of it as a one-dimensional hallway, and we don't know exactly where we are in the hallway, but we're trying to get to some, say my office along the hallway. If we're to the left of my hallway, we should go right to go to my office. But if we just keep going left and left and left and left and left, we're just going to go and get stuck in it's an infinitely long hallway, or it feels like an infinitely long hallway. We're just going to get stuck at the end. Whereas if we're to the right of my office and we go to the right, we also kind of get stuck. We need to go to the left to get where we're going. Once we actually get to the office, we have a reset action. The black action resets us with equal probability to one of those 3 states because, I don't know, we're drunk. And then we get to go again, try and get back to the office.
Okay, that seems reasonable.
Good. First, I want to point out, I think we talked about an example just like this before, and we said that probably the right thing to do is to go like left, right, that sort of thing.
Mm-hmm.
Because each time we reset, we're in one of these states. We go left, hoping that it's going to take us out of here, but that doesn't seem to work, so we go right to take us from this side back out. Actually, right, left is probably even better. Just keep doing this over and over and over again. All right, but now what we're talking about are memoryless policies. A memoryless policy has the form, when you're in the green state, well, there's only one action choice, so you take it. When you're in the clear blue state, you have to go either left or right, or maybe you can choose probabilistically among left and right. But you can't do these sequences because it's memoryless. You need memory to do a sequence.
Right. That's a problem. Okay, I see why this is a problem. Or you could just invent memory.
POMDPs do invent memory. If you're going to learn the POMDP model of this, it captures the memory that you need to actually make optimal decisions.
All right, fair enough.
So let's do this as a quiz.
Okay.
Here's what I want us to do. So one kind of memoryless policy that we could use in this example that actually kind of works okay is that each time we are in the clear blue state, we go left 50% of the time, we go right 50% of the time. So we actually just randomize. We flip a coin, and whichever, if it comes up heads, we go left. If it comes up tails, we go right. And so what will this do? Actually, if we're in this environment, what will happen is we're in one of the clear blue states, and let's say we're in this state, there's some probability that we'll actually get to the goal, and there's some probability that we'll actually go away from the goal. From here, there's some probability that we'll get stuck, not get stuck here, but we'll stay here for another step, and some probability that we'll get closer to the goal. And from here, again, there's a probability that we'll stay where we are or we'll go to the goal. And so it doesn't take that long. The average reward that we get, the average number of steps that it takes before we actually experience a reward and get reset, isn't that long, right? It's not certainly not infinite, and the expected value is some particular value. what I would like us to do is figure out, okay, can we do better than just a coin flip 50-50? What would be a way to actually get a better score? How can we randomize between left and right to get a better score?
Wait a minute. Before we say go, I just realized I had a question.
Okay.
This is a normal MDP, right? So what's your gamma?
Yeah, I think it actually would be helpful to give a specific value for gamma. Let's set gamma equal to 1/2 to make the calculations easy. And what we're talking about is, we were just in a green state, we got reset, and we're going to follow a policy which is some fixed probability of going left, some fixed probability of going right. What gives us the highest average discounted reward? And just once you get to the green, just stop at that point. Just consider the reward upon reaching the green state.
Okay.
So it's really very closely related to the number of steps.
Right. That's what I was thinking. You want to get the fewest number of steps. So for any value of gamma less than 1, greater than or equal to 0, it's really number of steps.
Yeah.
Okay, cool. All right. Okay, I think I got it. Okay, so I reassert my go. So go.
All right, so how do you go about solving this?
Well, I think there's like the right way of doing it, but then there's the way that I want to do it. And the way that I want to do it is I want to just ask myself, given that I just left green and I just saw blue, what should I do? Here's my reasoning. We want to do it in the fewest number of steps, so we always want to take an action that is likely to move us towards green. So if I have an equal probability of ending up in any of the clear blue states, then in one of them I want to go left, and in two of them I want to go right. And so I think a probability distribution of 1/3, 2/3 will get me there better than going 1/2, 1/2.
Yeah, so that's correct. I guess we can accept that.
Yay!
Maybe we should actually go through and convince ourselves that that we really do get a better number.
Yeah, I think that's fair. I mean, I'm pretty sure you get a better number. I'm not sure that that's the optimal thing to do.
Actually, I don't know that. I worked this again in my thesis. I worked this through in the case of average reward where there's no discounting. It's just we divide by the number of steps, the long-term sum of rewards. And that actually ends up being irrational. There's a square root of 2 in the probability that you need. This is going to be a little different, so maybe we should figure out what this one is.
Okay, sure.
So let's see if we can work this through. In the case of gamma equals 1, and probability of left is 1/2, and probability of right is 1/2. It turns out it will be nice to solve for the value function. So let's have 3 variables that represent the value function, one from each of those states. From the z state, what happens? Well, with probability 1/2, we go to the right, which ends up giving us an immediate reward of 0, and then we get a discounted value of being back in z. Or, with half probability, we go to the left, and we get our reward of 1, and we're done. So, z is 2/3.
Yeah, it's just boring old algebra. Oh, I see. You magically put 1/2 in where gamma used to be, because gamma is 1/2. That makes sense. Okay, fair enough.
I thought that would make things easier. All right, so z is 2/3. And let's work out x and y.
Okay, so I guess you will do a similar thing.
Yeah, so the value at x, from x with probably 1/2, we go to the left, which gets us a 0 reward, and then a discounted value of being back in x. Or, with probably 1/2, we get no reward, and then we have a discounted value of being in y. Meanwhile, y, the value from y, is, well, with probably 1/2, we get the discounted value of being in x, and with probability 1/2, we get a value of 1, and we're done.
So that's 2 equations and 2 unknowns.
Yes, linear equations.
It's even better.
So convenient.
Cool.
And some normal algebra-ish kind of things later. I have x is 2/11, and y is 6/11. Better to be in y. So when we average our expected reward, our discounted expected reward from each of these possible starting states, we get 1/3 of this and 1/3 of that and 1/3 of that, or 0.4646 as our value for taking this stochastic policy.
That's not even 50-50. Ha!
Okay, and we said that we could do better. So let's we said we could do better by choosing probability of left to be 1/3 and probability of right being 2/3, right?
Yeah.
All right, so let's see if that actually gives us a better number.
Okay.
So we need to work out what the value of z is in this case where we're going 2/3, 1/3. So once we solve through for z, we find out that z is 1/2. Before, z was 2/3. And so we actually are doing worse in this state because we're spending more of our time bashing against the wall to the right.
Yeah, grad school.
And we're going to write down what happens from these other 2 states. So the value at x, which simplifies to 5x equals 2y. And the value at y is, again, we're going to go to the left 1/3 of the time, getting us the value at x. And we're going to go to the right 2/3 of the time, getting us our value of 1. All right, so once we solve all that through, we get y is 5/7 and x is 2/7. And so when we average these 3 values out, we actually get 1/2, which is a little surprising to me that the 7s kind of cancel out. But 1/2 is bigger than 0.464646, so we actually have a better policy.
Right, and coincidentally, it does give us 50-50.
What do you mean it gives us 50-50?
Well, you said you wanted to do better than 50-50, 0.5, that's 50-50.
No. The 50-50 policy, which gets us 0.464646, we did better than that policy by trying a different policy that actually gets 0.5.
I know, Michael, I was using wordplay.
Ah, brilliant.
Thank you. So I suppose using all of that algebra, we could actually figure out what the optimal numbers are if they aren't 1/3, 2/3. Maybe they are, just by replacing all the 1/3 and the 2/3 with p and 1 minus p. And we'd figure out what p is.
Yeah.
And I'm sure that would be a wonderful exercise for the students to do.
All right, so we'll leave it for that then.
Excellent.
Now that we talked about doing reinforcement learning in a POMDP setting, we're actually now going to talk about a much weirder combination. We're going to talk about how we can think of reinforcement learning as actually being itself a POMDP.
Okay.
This is an area that is often referred to as Bayesian reinforcement learning. The idea is that we're going to keep a Bayesian posterior over possible MDPs that we're in, and we're going to use that to actually optimally balance exploration and exploitation. So we're actually going to behave optimally, and reinforcement learning becomes planning.
Okay, so does it mean we're going to use Bayes' rule?
Well, I guess technically, in that whenever you compute a posterior, you're actually doing something like Bayes' rule. Yeah. So, but maybe this is not so clear. Let me try to draw a picture. So I'm hoping this example might make things a little bit clearer. So let's consider a really simple reinforcement learning problem. We've got two states, state 1 and state 2. Two actions, a black one and a, I don't know, purplish kind of one. And so if we were doing reinforcement learning in this environment, like, and you were, say, the reinforcement learner, what would you do? Let's say we're in state 1. What would you do? Would it be better to do purple or black?
I don't know.
Okay, so then what would you do?
I'd pick one of them.
All right, so let's say you pick black.
Okay.
And then we observe a transition, and ultimately we can sort of build out a model or use Q-learning or something like that to work out the values. So what I'd like to do is actually try to have you think about this like a POMDP. And I think a simpler way to show you that would be, instead of imagining all possible MDPs that this could be, let's just pretend it comes from a small finite set.
Okay. Are there any small sets that aren't finite?
No.
Good. Then I think we're on the same page.
All right. Then I agree with you. So here's the set that I had in mind. We've got 3 possible worlds that we're in, A, B, and C. So these are 3 possible MDPs, right?
Okay. And they all look exactly the same to me except where you get reward.
Yeah. So it just so happens that the actions all do the same thing in all 3 of these. And we know that. We just don't know where the reward is. Is the reward something you get for purple when you go from state 2? Is it something that you get for purple from state 1? Or is it something that you get from taking the black action from state 1? And we don't know. Now, if you had to solve this reinforcement learning problem, it's kind of a reinforcement learning problem, right? You're in some state. You get to see which state you're in, 1 or 2. You can try actions black or purple. And what you're trying to do is actually figure out how to maximize reward. But now that it's just a finite set of possibilities, we can think about this like a POMDP.
Sure. And in fact, I think this one's pretty straightforward. If I'm in state 2, I know what I should do.
And what is that?
I should take the purple action.
And why is that? Explain.
Because I either immediately get reward for it, or I know that I get reward for being in state 1. And then when I'm in state 1, well, actually, it's not clear which one I should do.
All right. So let's do 2 things. Let's start off by just tracking belief states in this, because I think that's already kind of an interesting problem in and of itself. What we're thinking about here is that we're in a POMDP with 6 states. If in state 1, but we don't know which MDP we're in, then the belief state's going to look something like this. Agreed?
Agreed. If this is where we're starting and we know nothing else and we haven't done anything yet, then we can be in any of those states, presumably with equal probability.
Good. All right. So now the question is, if you were to do the purple action from here, what would your expected reward be?
My expected reward would be 1/3.
Right. So if we happen to have been in MDPB, which we don't know if we are, and we took the action purple, we'd get a 1. If not, then we'd get 0. But what also would happen if we get the 1? What's our new belief state?
If we get the 1?
Yeah.
Well, then we know that we are in B1.
Good. B1. Right. So we're in this state. So the belief state becomes basically fully observable at this point. We know which MDP we're in, and we know what state of that MDP we're in, and we can just execute the optimal policy for that MDP, which in this case, as you might guess, is just purple all the time.
Purple all the time. Purple all the time. Yeah, I agree.
Excellent. So let's make sure you get this. We'll do a little quizzy kind of thing.
Okay.
So here's the question. What happens if we start off in state 1, we know we're in state 1, we don't know which MDP we're actually in, we take action black, and we observe no reward? How does that actually change the belief state? Where do we think we are at that point?
I don't know, but I think I can figure it out.
Awesome.
Excellent. Okay, so is there anything else you need to tell me? Do I know everything I need to know?
I feel like you do. I have the discount factor as a half, but I don't think you need that for this question. And this is the current belief state, so you know that. So I feel like there's enough information.
Okay, well, we'll find out. And if not, we'll fix it in post. All right, you ready?
Ready.
Okay, go.
All right, so how should we think about this?
Okay, I think this one's fairly straightforward because determinism. So at least for state 1, no matter what you do, if you take the black action, you will end up in state 2. That means that I know right away that my belief for being in state 1 will be 0.
Good.
So I can just go ahead and put those zeros in. But you also told me I got a reward of 0. Well, if I have a reward of 1, then I would end up in state C2. Since I didn't get a reward of 1, I cannot be in state C2. Therefore, that's 0. And since there's nothing else to distinguish state A2 and B2, I have a probability of 1/2 and 1/2.
All right, so why is it not a third,
It's a third, but then normalized.
Right, because of?
Because of the fact that you have 0 probability of being in state C.
No, but what if we were actually deriving that probabilistically? We would use...
Probability?
I want to say Bayes' rule.
Well, sure.
Yeah, and so, because you asked before if this had anything to do with Bayes' rule. And so Bayesian RL actually does have to do with Bayes' rule in the sense that we're tracking the likelihood of different possibilities, and the way that we do that is we make a transition, observe what we observe, and then renormalize. We use the Bayes' rule trick.
Right, well, that was basically what I was saying. Thank you very much. I'm here all week.
So so at this point in time, we would actually be sure that we're not in MDPC, but we could be in A or B, and they're equally likely. What action do you suppose we should take from here?
Actually, from here, we should take purple.
Yes.
In fact, we have to take purple because we know that we either get a reward immediately,
right,
or we end up in a state. We know which state we're in.
Right.
Actually, no matter what we do, after we take purple, we'll know whether we're in MDP A or B.
Right.
And if we're in MDP A, great, we got reward of 1, and we should just go back and forth. If we did not get a reward, then we know we're in MDP B, and we should just keep taking purple from that point on.
Yes.
So that points something out to me.
Okay.
We had everything we needed for this quiz, right? But if we had started out in the purple state, and you told me that we took the black action
and got a reward of 0,
that I need to know what state I'm ending up in.
That's right.
I think.
Yeah. So I really should write, state 1, action black, and then we observe reward 0, and we observe that we're in state 1.
Or state 2.
In this particular case, state 2.
Okay.
And by state 1, I mean state 2.
Okay, good. I get it. So, right, because even though we're turning this into a POMDP, there is an MDP. Our observables are actual states. And so you need to know what the observable is to update your belief state in general.
Right. And so so when we represent this as a POMDP, we're actually saying that states of the POMDP are the 6 states, as we talked about. The observations are the rewards, the possible rewards, 0s and 1s in this case, and which state we end up in, blue or purple, 1 or 2. And we don't know which state of the POMDP we end up in, but we know which state of the underlying MDP.
Whichever one it is.
Whichever state it is.
Right.
So what does an optimal policy mean in this setting? Like, what does it do?
Well, I think that probably depends on the actual things, but what I want to say is that it's the thing that allows you to figure out which MDP you're in so that you can execute the optimal policy.
So it tries to figure out which MDP it's in, because that might matter for optimizing a reward.
Right.
But it's balancing that against, well, maybe along the way of figuring that out, we have opportunities to get high reward.
Right.
Which is to say exploit. So we usually, or at least so the way we've talked about it so far, we make this distinction between explore and exploit. And what's neat about this POMDP way, or this Bayesian way of thinking about reinforcement learning, is this goes away, this dilemma goes away. It's no longer I'm trying to explore or trying to exploit. It's I'm always trying to maximize reward. And maximizing reward involves possibly taking actions to gain information, which is to say exploring, but it's mixed in with actually getting the rewards. And in fact, the optimal POMDP policy for this gives you the optimal reward. It just so happens that some of the time that involves some exploration, some involves exploitation, but that the algorithm doesn't make that distinction. It's just maximizing reward.
Right, because it's not exploration of the POMDP, so to speak. It's exploration of the underlying MDPs you might be in. And so you're always exploiting in some sense.
You're always exploiting, but you're exploiting in belief space,
Right.
which causes you to actually sometimes gain information or make your belief state get more pointy, right? More specific to where you actually are.
Right. I like that. How would you figure this out, though? How would you figure out what the right... So you asked me what the optimal action would be.
Right.
And I figured it out using proof by staring at the screen.
Nice.
But it seemed to me that that's not necessarily an algorithm.
Okay. So if we needed to find out the optimal behavior, let's say from this belief state, the 1/3 0, 1/3 0, 1/3 0, what would you do with your computer to figure it out? Like, you don't have to tell me the exact answer, though I think I know it.
Well, I would search.
Sure, search, but like it's a POMDP, so we just need to solve the POMDP.
Right, sure.
And so we talked already in this lesson about various kinds of algorithms for solving POMDPs. In particular, doing like value iteration with piecewise linear convex functions, that sort of thing.
Okay. I guess that works out to be the same thing. Fair enough.
Yeah, and so this works in general as long as the space of possible MDPs is finite, but it's not generally finite.
Oh, so then does something else work in general?
Yes and no. So what I'm basically arguing here is that we can think of reinforcement learning as a kind of planning. It's not learning at all. It's actually planning in a kind of continuous space POMDP, where the hidden state is the set of parameters of the MDP that we're trying to learn. Now, there's an infinite number of those, which makes things a little bit awkward, and so we don't really get the piecewise linear and convex property anymore, but it can be shown that you can actually get a result that shows that the value function in this continuous space POMDP is actually piecewise polynomial and convex.
Okay.
You know, it's not as nice as linear, but it's still representable.
How big is the degree of that polynomial?
It grows with iterations of value iteration.
I see.
Yeah. So it's not like piecewise cubic and convex. It's like piecewise, it could be a lot of degree, depending on how many iterations you do. So this is still pretty awkward to work with. There's an algorithm that actually works fairly nicely called Beetle that tries to approximate this piecewise polynomial and convex function and can sometimes actually end up learning very good approximations of the optimal way to do reinforcement learning for those spaces of problems.
Does Beetle stand for something?
Bayesian exploration trade-off in learning.
Which is cheating. I think we agree.
I think we agree, yeah, but otherwise it would be like Beetle, which would be just way too hard to say.
Bayesian exploitation trade-off in learning everything.
The E for everything.
Yeah, and then that would be better. And I think I could forgive that.
Learning excellently.
No, it's too many. That's just absurd.
The point that I'd like to make, though, or the point of this slide, is that there are Bayesian RL algorithms. Beetle is one of them. It is not by any means the only one. There's lots of different ways that people have looked at actually keeping Bayesian posteriors over the MDPs that are being learned, and then trying to use that Bayesian posterior to make better decisions than you would in just reinforcement learning, where you don't have any kind of prior, any kind of structure on what the possible underlying MDP is. So a lot of people really like this stuff. It seems to, at the moment, be on the side of just kind of too expensive to be practically useful. Q-learning seems to tend to win. But it's very elegant, and it's a useful way of sort of realizing that planning and learning actually are two sides of the same coin.
We've used it before in some work that I've done.
Oh, okay.
But what we were taking advantage of is the fact that it gives you probability distributions over value functions, or rather over Q functions.
How does it do that?
You're in a state, and it just tells you basically the probability of an action being optimal. And that turns out to be very nice, because you can then compare various sources of information together, because they're all, if you can make them all look like probabilities.
Oh, that sounds like that really cool policy sort of merging paper that I saw.
Yeah, that one.
Is that you?
Yes, by Isabel and his colleagues.
Woo! All right, so the last topic I'd like to cover in POMDP land is a line of work that I am somewhat fond of, that is called predictive state representation. So let me say a little bit about the motivation behind studying this, and we'll talk a little bit about the representation itself, but we're not going to talk much about algorithms that actually make use of this. There is a literature if you want to dive in. All right, so here's the basic premise of this line of work. So we talked about POMDPs. So POMDPs, when we're moving around in a POMDP, we're tracking the belief state, which is a distribution over states, right?
Right.
So here's the thing. The states are not observable, right?
Right.
So how can we ever hope to learn in a POMDP when we never actually get to see these underlying states? They're never observed. So you could ask yourself, do they even exist? Or are they just kind of useful fictions of our imagination? There's nothing that we can ever do to test, hey, was this the state we were actually in? The answer is, I don't know. I mean, if we're learning in a POMDP, we're just creating this notion of states to provide some structure to the observations that we've seen.
Is this like a tree in the forest thing?
Yeah. If a POMDP is solved in a forest, does anybody know whether or not they exist? And the answer is, me.
No, I think you're right. I mean, we're making this stuff up anyway, right?
Yeah, and in the case that somebody gives us a POMDP and says, would you please plan in this? It's a reasonable representation to work with. But if you're in a reinforcement learning setting, you never get to see these underlying states. You can never actually collect statistics about them. In fact, most of the good work that I've seen that uses POMDPs, they don't learn the POMDP. They actually send I'm going to say grad students out into the field to measure underlying states and then measure the observation function. They actually kind of instrument the world to build the POMDP, and then they can act in the POMDP successfully later. But it's just there's really no good way to learn about the states.
Or even that they're real.
Even that they're real.
Okay, so now that you've blown my mind, what does it have to do with predictive state representation?
All right, so the idea of a predictive state representation, or a PSR, is that the thing that we're going to use for representation isn't going to be probability distributions over these possibly fictional states, but instead they're going to be probabilities of the outcomes of future predictions. So like I'm in a state where it's about an 80% chance it's going to rain tomorrow.
Okay, which doesn't require an actual state.
Well, and that was maybe not a great example. So let me give a more concrete example to kind of ground this idea out. So here's an example that we're going to use to kind of motivate this idea. So here's a representation of a POMDP. It's got how many states?
4.
Good. It's got how many observations?
3.
Right. Blue, green, and red. So these two states are indistinguishable by their immediate observations. And let's say there's 4 actions, north, south, east, west. So north from this red takes you to this green. North from this red takes you to this blue. East and west from this blue leave you where you were, etc. Does that make some sense?
Yes.
So we've got left, right, up, down as our actions, and these 4 states and these 3 possible observations. And so we can represent this as a POMDP if we know these dynamics, we know this system, we know this model. We can represent, what's the probability we're in each of these states, 1, 2, 3, 4 of the states. And so, for example, if I say, okay, I'm going to start off uniformly at random. Oh, and by the way, the state you're in is currently red.
Mm-hmm.
So then our belief state would be what? 0, 0. A half. If we then go left, then our belief state would be 0, 0, a half still.
Right.
If we went up and observed green, then our probability distribution would be 0, 1, 0, 0. We'd definitely be in this state. Mm-hmm. And actually, given that there's no stochasticity in this case, we would know where we were forever after. Right? We can continue to act, and we'll know where we are. We're going to try to re-represent this same idea, the same system, the same model, but not using a POMDP, but instead by using a set of predictions. So I'm going to claim that the tests that we're going to use for this representation, there's lots of possibilities, but what we're going to do is say, hey, what would happen if you were to go up? Would you see blue? So what's the probability that you'd see blue after going up? And if you were to go left, would you see red? What's the probability of seeing red if we were to go left from the current state? And so again, the state is going to be predictions, is going to be probabilities on these 2 quantities, and we're going to try to keep that updated. We're going to keep these predictions updated as we move around in the environment.
Okay, so we're replacing a distribution over states with a kind of distribution over the outcomes of tests that we might take.
Yeah, I think that's a good way to think about it. It's this probabilities that we get here don't necessarily have to add up to 1, right? It's sort of independent. The question of how likely is it to see blue when we go up, how likely is it to see red after we go left? But other than that, it is a sort of probabilistic quantity. But we kind of like this notion that these tests are actions and observations, because at any given time we could say, hey, this seems like the kind of situation where it's 2/3 probable that I go up and see blue. Let's just try that just to make sure. So we can go up, see whether or not we see blue, and see how often that actually seems to happen. It's still not trivial to learn in this case, but at least it's grounded out in observables, actions and observations.
Right, and I guess sort of philosophically, if I might wax philosophical for a moment, there's really no difference between this and states, right? Because if states are kind of made up things, which represent states of the world, dare I say it, then these tests also kind of represent, at least implicitly, other states of the world, and they're just as fine or as reasonable a representation as these made up nominal circles.
Yeah, they're not certainly no worse, but I'm going to argue that in principle they might even be better, because again, you can actually execute these tests and see what the outcomes were.
And then that'll tell you where you were and possibly where you are.
Yeah, or at least would let you validate your current predictions. Whereas with states, if I think, okay, I'm in the belief state 0, a half, 0, there's nothing that you can validate. There's no test that you can run. There's no experiment you can do in the world that would tell you what the states actually were, because states are not observable.
But these tests can tell you sort of whether you are, I'm going to try to ground this out in an example. So, am I sick? Do I have a particular disease? Well, there are tests that I could run that would tell me, and then I might be able to do other more interesting things. And that's kind of a practical thing to know rather than asking the question. I mean, it's one way of sort of answering an underlying question of, am I in the state of being sick or in the state of, I don't know, having blue hay fever.
I guess that's this upper left state.
Yes. So I'm intrigued. So what's next? What do we do with these tests?
Well, so in principle, we should be able to learn PSR representations. And because, again, if we have a test, we should be able to validate it and make our predictions better over time. And in principle, we could plan in this kind of space as well. We're not going to talk about either of those in the class, but I do want to do a slightly more concrete example of these test probabilities with this little grid that we've got going here, just to make it more concrete.
Okay.
What I want to show is that we can actually kind of potentially move back and forth between belief state type representations and predictive state type representations. So let's imagine that we have this environment here that we've been talking about, and the belief state is, well, it's 0.1 probability of being here, 0.2 probability of being here, 0.4 probability of being here, and 0.3 probability of being here. Could we use this information to actually work out the probabilities for these predictions, what these predictions ought to be? So from this belief state, how likely is it that I'm going to see blue if I take action up? And how likely is it that I'm going to see red if I take action left? So do you think you can work out what those numbers are just from the information we have here?
Yeah, I'm pretty sure I can, actually.
You want to give it a try?
If you insist.
I'm going to insist.
All right. Well, let's go.
All right, so how are we going to do this?
Well, I'm going to do it in the most methodical way I can think of. I'm just going to say, well, for each of those states, what's the probability of test 1 coming out such and such and test 2 coming out such and such?
Good.
And then given that, I can just multiply that effectively by the belief state and I can get predictive states.
Very good. All right, so what's the probability that if we were to go up, we would see blue from each of the 4 states?
Okay, so it would be 1, 0, 1, 0.
Good. All right. And so if we were now to combine these, I guess it's a dot product, right?
Yeah.
It's the dot product between the probability of the different outcomes times how likely it is that actually is the state that we're in. Mm-hmm. So that should be really easy. That should be like 0.5.
Yes. For
the first prediction. It seems like we should be able to do something pretty similar for the second one.
Yes. So what's the probability that I go left that I will see red? It is 0, 0, 1, 1, 0.7.
Cool. All right. So that wasn't so hard, right?
And it doesn't add up to 1, to your point.
Which is what I was saying before. That's right. Yeah. So because each of these predictions are kind of an independent thing. So it's not like a distribution over what prediction we're going to do. It's more, as you said it, which I thought was really good, a distribution over the outcomes of the test, right? So in this case, we'll either see blue, red, or green after we go up. So the probability of up blue, up green, and up red, that'll add up to 1. But turns out we didn't need those other tests to represent things in this particular example.
So I just noticed something while I wasn't listening to what you're saying, which is that I can go from belief state to predictive state, but I can't go from predictive state to belief state.
So why don't you say what you said again? Let's look at the problem the other way around. Let's say I know the predictive state is 0.7, 0.6. So we know if we were to go up, the probability we'd see blue is 0.7. If we were to go left, the probability we would see is 0.6. Can we figure out the belief state using that information?
I'm going to claim that we can come up with a belief state that is consistent with that, but there is not a unique belief state that is consistent with that.
So we just looked at an example where we had a belief state that gave this as the predictive state. Can you give us another one? Can you give us a belief state where we get the 0.7, 0.6, but it's different from the one that we just looked at?
Well, I don't even think I have to do that. Let's just pick the one for 0.6, right? So with 0.6, what's the value of a test in each of those states? So let's just take test 2, and we know that it is 0, 0, 1, 1, right? Mm. So we know, as you pointed out before, we just have to do a dot product with the belief state and those 0, 0, 1, 1 up there, and we add it up together to get our predictive state.
Okay.
So we got a value of 0.6, right?
Yep.
Well, since the 2 reds are 1, then that means any belief state in the bottom row that adds together to get me 0.6 will be correct. right?
Well, it'll give us that prediction for
It'll
sure.
give us that prediction for sure.
So let's
pick a belief state.
sure. So
How about 0.3 and 0.3?
I was thinking that too.
So we agree that would give us 0.6?
That would give us as a prediction for test number 2, 0.6.
Right. Now what if it were 0.3, 0.3, but instead 0.2 and 0.4?
That would also give us 0.6.
Right. And I'm going to claim that since all we're doing is taking two numbers and adding them together to get a third number, there's an infinite number of those.
But we're not done yet because we didn't do test number 1. So our current predictive state says we're in a situation now where both test 1 has a probability of 0.7 and test 2 has a probability of 0.6. So there's additional constraint there.
Okay, cool. So we have 0.3 and 0.3.
Yeah.
Which leaves us with 0.4.
Yes, which would have to be there.
No, we have a total of 0.4 that we can play with, right? So the top row has to add up to 0.4.
No, the side column has to add up to 0.7, right? Because we're saying that if we were to go up, we would see blue. That means, and the probability of that is 0.7, which means the sum of the probability of being here and here is 0.7.
Right.
So we know what the probability of the upper left state is. It's what's left over after we pick the 0.3.
And then that means the one in the upper right has to be
0.
Which is what I was saying. What I was saying is that the total, all four of those numbers have to add up to 1.
Got it.
So you get 0.3, 0.3, 0.4, 0. Great. You're right. So now we have one belief state. Now what if I made it 0.2 and 0.4?
Yeah, good.
So now if I made it 0.2 and 0.4, then we know that has to be 0.5.
Right.
And that has to be whatever's left.
Yeah, negative 0.1.
Oh, so that's not even possible. So what if I made it 0.4 and 0.2 at the bottom? So that has to add up to 0.7. So it has to be 0.3. And that gives you 0.9. So I have 0.1.
I see what you did there. So now we actually have two different belief states that would be consistent with that predictive state.
Right.
So what do you suppose we do in a predictive state representation to make it more complete, make it more equivalent?
I don't know, but I think you're going to tell me.
I am going to tell you. So we need more tests. So it turns out that if we have enough tests and the right tests, then knowing the outcomes of those tests gives us a bijection with the belief states. We can always go, any belief state is going to give us one of the predictive states. Any actually achievable predictive state is going to give us a unique belief state. The 2 tests wasn't enough to do that. In this case, we definitely don't need more than 4.
So does that be generally true? You never need any more tests than there are states? Is that true?
So funny you should say that, because we have a thing that I'm going to call the fundamental theorem of PSRs, but we could just call it the PSR theorem, that says specifically any n-state POMDP can be represented by a predictive state representation,
or PSR,
with no more than n tests, each of which is no longer than n steps long.
Oh, so that's good. But also you just introduced something, the number of steps. I guess I didn't think about that before, since both of those tests were sort of...
They were very short, right, yeah. But, and it's not hard to come up with an example like that, right? And I'm writing it as a POMDP because I am a, limited beast. And it's hard for me to think about PSRs. So what might a test be that you'd need to represent, POMDP written like this? So we've got, white state, black state, black state. So one-step test would be things like, if I go, well, there's only that one action, and I see white, what's the probability of that? That's not enough information to know where we are, right?
Right.
And in fact, seeing black is also not enough in this case. We actually have to think about what happens in 2 steps from now.
Right. So yeah. So you could say if your test is 2 steps away, then I could, for example, figure out if I see a white and then I see a black, then I know I must have been in the bottom state.
Right.
If I see black after making one move, then I had to be in one of the 2 middle states.
Right.
And I guess if I took 2 steps and I saw white twice, then I know I had to be in the top state, for example.
So are you saying that you think we need another test to make this go?
Well, I don't know. I'm just occurs to me that I can figure out that I'm in the top state if I see 2 white ones. That's all. I'm just pointing that out.
Well, wouldn't it be enough to just know, okay, if I go up, will I see white and then go up and see black? If the probability of that is 0 and going up and seeing black, the probability of that is 0.
Oh, so if going up I see black, the probability is 0, then I have to be in either the top state or the bottom state. And if it's also the case, if I will not be able to see white and then black, then that tells me which state I must be in.
Yeah, that was the thought.
Right. Yeah. Sure.
But these longer tests are really important here. Just having the single step doesn't give you enough information, doesn't give you enough constraint.
With those 2 tests, can I alone figure out everything? Can I completely disambiguate it?
So I think it's like the other example that we looked at, which is if we know that we're in one of these states, top, second, third, fourth, then I think these two tests are enough to tell us which of those four things we're in. But in general, a belief state might be something like, well, 0.6 of the top one and 0.2 of the second one and 0.1 and point something else. So in that case, we've got a four-dimensional vector, actually a three-dimensional vector because it has to add up to one, that we're trying to specify by way of two numbers, and we get that same kind of indeterminacy that you worked us through in the other example.
I see. Okay. So this kind of makes me want to ask a question.
Okay.
Why does this help? Why should I bother going to PSR other than the mathematical niceties?
There are some examples where it helps, and part of it is a philosophical thing that it's got to be better for us in the long run to represent our world in terms of things that we can actually observe instead of things that we can never ever observe. So that's kind of the philosophical point that this answers. There is, as far as I'm aware, the literature that I'm familiar with in terms of learning a POMDP, you can learn a PSR representation maybe easier than learning a POMDP representation, but the thing that I find interesting is that there's POMDPs that are easy to learn and there's POMDPs that are hard to learn. And the POMDPs that are easy to learn as PSRs, and the POMDPs that are hard to learn as PSRs. So there's almost sort of this underlying toughness of the POMDP itself, or of the environment itself, that switching to PSRs doesn't seem to exactly help. There is a case though when certain of the attributes of the problem are continuous, where in fact it can be shown that a PSR representation can actually be learned efficiently when the POMDP representation is not clearly learnable efficiently.
I mean, I suppose one nice thing about the test model, like at least in a particular case where, there's like some 1 or 0 probability of a test coming out under certain circumstances, it might be easier to think about what you ought to do in order to figure out exactly where you are. Like the set of tests you might run so that you can completely determine where it is you are. In the real sort of underlying world.
Just knowing that might be a useful thing. Yeah, for control and discovery.
Right.
Yeah, I mean, I'm not familiar with papers that do that exactly.
Yes, you are.
Do you have a paper that does that exactly?
Holmes and Isbell?
Guess I wouldn't think of it that way.
I always thought of it that way. Or at least Satinder told me that I should think about it that way. I didn't think about it that way till he told me I should.
And that, in particular, that's Satinder Singh, who his group did a lot of the pioneering work on PSRs and had some very nice analyses for how they worked. So yeah, okay, but I just wanted to give kind of a sense of this. There is some more recent work using least squares methods instead of probabilistic methods that actually can lean on this PSR idea to learn efficiently, actually. If you have enough data, it can actually turn it into a model that predicts well. And the model has elements in common with PSRs. So it has gotten some leverage. I think the jury's still out as to whether or not this is really the way we want to represent our environments, but it's a useful tool for the toolbox.
Yeah, I can see that.
So that actually brings us to the end of the POMDP topic. So
how do we know we're at the end of the POMDP topic?
We have high probability of believing that we're at the end of the POMDP topic because the observation that we're making is the what have we learned slide. So what have we learned?
Well, we learned about POMDPs.
Partially observable Markov decision processes.
Well, we had been exposed to these things before, but we really kind of dove into sort of some detail about what they are and how to solve them. And in particular, we've talked about belief states. As kind of a representation, which represents the states that we might be in and how much we believe that we're in them. We talked about POMDPs as a strict generalization of MDPs, which is sort of important, and that if we can solve a POMDP that happens to be an MDP, we will solve the underlying MDP. One of the unfortunate consequences of all that is that dealing with POMDPs is hard. They're hard to solve. They're just sort of fundamentally difficult. I can't remember the exact result now, but there was something in there about undecidability.
Yeah.
And that was difficult. That was hard for me to deal with.
It was hard for you to accept. Hard to accept.
Right. Despite the fact that it's hard, we did come up with some algorithms for solving MDPs, like value iteration. I remember something about piecewise linear and convex.
Right, representing value functions as piecewise linear and convex functions.
Or PWLC. And one of the things that was nice about that is that you showed that you could build up these sets of kind of linear functions, and because you only cared about the max at any given point, you could throw away a bunch of them that might be unnecessary. Good. And sort of keep the hard problem possibly manageable.
Good.
That was really nice. Then we went from the solving of POMDPs to reinforcement learning with POMDPs. And if solving POMDPs is hard, then RL for POMDPs definitely has to be hard. And that turns out to be true. But we tried to do it anyway. Let's see, we did memoryless.
First, we talked about a model-based method.
All right, model-based method.
Where you try to actually learn the POMDP from experience wandering around in it.
Right.
And do you remember how we did that learning?
With a great difficulty?
Well, sure. We talked about expectation maximization as a way of trying to organize that computation.
Sure, that's a favorite of my expectations.
Your maximally favorite?
Yeah, my maximally favorite one. We got to go all the way back and try to remind ourselves how EM worked.
Yes.
That was fun. And then we did memoryless?
Yeah, and we needed, in the memoryless case, we might need to be random.
So again, just like grad school.
I don't think that's true. You're saying that if you're in grad school, but you don't remember where you are in grad school, then it helps to act randomly.
Well, it certainly explains the behavior of some of my grad students. Okay, then we had, we probably did more stuff there, but I can't remember it. And so I do remember, though, that we started talking about Bayesian RL.
Yes, and the cool thing about Bayesian RL being that it blurs the line between planning and learning. So, and Bayesian stuff does that in general, this sort of notion that, well, all learning really is estimating probabilities of things. It's not actually, learning. So it just keeps changing your posterior. And so decision-making in the Bayesian RL setting ends up becoming just a kind of version of planning in a continuous, ugly kind of POMDP.
Speaking of which, if we have Bayesian RL, do we have frequentist RL?
Well, sure. I mean, Bayesian and frequentist are kind of, rivals in a sense. So anything that's not Bayesian maybe is frequentist.
Okay.
So all the other reinforcement learning that we did, like Q-learning and whatnot, it certainly has a frequentist flavor in that, what is frequentist statistics is about? It's about, counting up how many times something happens and divided by the number of times you asked. And that is, definitely Q-learning has that flavor. Model-based RL where you're trying to estimate the parameters of the model from experience, they tend to have that flavor.
Okay, so good. So then we have been learning about frequentist RL, and now that we have Bayesian RL, it reveals the frequentist things that we had been doing in the past. So I'm okay with that.
Yeah, and the Bayesian RL is very nice because it doesn't make an exploration-exploitation distinction anymore. You're always acting given your knowledge of what the truth is, and you're acting in a way that maximizes your reward given that knowledge.
Right, and so exploration is exploitation. Ooh.
Planning is learning. Exploration is exploitation. War is peace.
And we have always been at war with supervised learning. Okay, and then the last thing is PSRs, or predictive state representations.
Yes, indeed. And the upshot of the PSR idea was what?
Well, that rather than thinking about states, which might not even exist, and even if they do exist, you never know where you're in them or not, so really, they don't exist in some very important, insane potato sort of way. What does make sense to think about is whether there are specific tests that you could take that would then predict what you're likely to observe, and that in some sense that's a very satisfying way of thinking about the world, that I need to kind of keep track of, well, if I were to do certain things now, what would happen? And that was kind of the push for sort of PSRs. And insofar as you prefer that kind of way of thinking about the world, the nice thing is that PSRs can represent any POMDP, and so they're equivalent.
Right, except maybe more palatable philosophically or so forth. Certainly Rich Sutton was pushing people in the direction of this representation for that reason. There's a kind of philosophical stance that says, am I sick? Well, what does it mean to be sick? It means that I, could be dead tomorrow. I could be stuck in bed tomorrow. I could be running a fever. It's like there's a bunch of observable things that are a function of what the current state is. And so it might be useful to talk about things in terms of what those predictions are as opposed to positing some kind of magical internal state.
Well, this makes sense, right? Because the only usefulness, if you go back to that, and we talked about this on our last machine learning course, in some sense, the only usefulness of a state is what it allows you to predict about what's going to happen next, little made-up objects. So the only reason it's worthwhile even recognizing something as a state is it allows me to distinguish between something else that might be important later.
So another one of our, universal contradictory truths is that states and predictors are kind of the same thing.
Yeah, all things are the same.
Excellent. All right, so I think that's the last lesson that I was doing by myself. I think I'm going to turn it over to you for the next one.
Well, I will point out that you've done none of this by yourself, Mike. We've done this together.
That's fair.
All right, well, with that, I guess we should say goodbye.
All right, see you next time.
Bye.